Welcome to Summarize Science, where we break down complex research into simple terms. Today, we're talking about terahertz waves, a mysterious part of the light spectrum that could revolutionize everything from communication to medical imaging. The problem is, making devices that can create and control these waves efficiently is incredibly difficult. But what if you could use a special material that's both magnetic and has unique electrical properties? Researchers in this paper looked at a material called bismuth ferrite to do just that. In their first experiment, they took a thin film of this material and hit it with a super-fast laser pulse. The material responded by emitting a clean, narrow-band pulse of light at about 2 terahertz. This was interesting, but the real magic happened when they added a nanometers thin layer of platinum on top. Suddenly, a second, lower-frequency signal appeared, between 0.4 and 0.8 terahertz. This new signal was the key, and they found that its frequency wasn't fixed. In fact, they could precisely tune the frequency just by changing how thick the platinum layer was. Look at this graph. As the platinum layer gets thicker, from 1 to 6 nanometers, the peak of the Terahertz emission shifts to a lower frequency. This is a huge discovery, a simple, tunable source for these elusive waves. So, how does it actually work? The laser doesn't just pass through the platinum, it heats it up incredibly fast, creating a tiny, powerful vibration. This creates an ultrafast strain wave, essentially a microscopic sound wave, that shoots into the bismuth ferrite below. This isn't just any sound wave, it's powerful enough to interact with the material's internal magnetic structure. This interaction, a dance between sound and magnetism, is what generates the tunable Terahertz light. By changing the platinum's thickness, the researchers changed the pitch of the sound wave, which in turn tuned the color of the Terahertz light. They confirmed this wasn't happening in other materials, showing this effect is unique to the special properties of bismuth ferrite. So let's recap the amazing discoveries here. Researchers found that by adding a thin layer of platinum to bismuth ferrite, they could generate Terahertz waves, and crucially, they could tune the frequency of these waves simply by changing the thickness of that platinum layer. The mechanism is a fascinating magneto-acoustic effect where an optically generated sound wave drives the magnetic dynamics of the material. What does this all mean for the future? This work establishes a new and versatile way to build engineered, on-demand Terahertz sources that work at room temperature. This could be a foundational step towards practical Terahertz technologies like ultra-fast wireless communication far beyond 5G, more sensitive security scanners, or new kinds of medical diagnostic tools. The ability to tune light with a tiny film of metal opens up a whole new field of possibilities. Thanks for watching Summarize Science.